So a very common question is, how much power do I lose because of harmonics? And do I pay for harmonics on my power bill? So let's back up and talk about power in general and what we pay on our power bill. There's multiple different things that we pay for. One is work, which is watts. We know that we pay for watts, kilowatts, kilowatt hours. We'll talk about that. But work that we do with watts is things like lifting an elevator, moving a motor, things like that, creating heat, things that actually do work. Okay, the second thing is VARS. And VARS we call reactive power, or sometimes we call it imaginary power or magnetic power. Magnetic power allows a motor to spin, but once you overcome friction, you're not really doing work, so to speak. You're just creating a magnetic field. And then there's VA. VA is a combination of volts times amps. And volts times amps gives us apparent power, which is a combination of watts and VARs together. And we'll talk a little bit about that in the power triangle and how that relates to power factor. But then the final part here is harmonics. So it's not watts, it's not VARs, but it is related to VA, and specifically it's related to the amps. So let's take a look at the power triangle, but in a three-dimensional version here. So if we look at, on the x-axis here we have kilowatts. On the y-axis we have kVAR. On the hypotenuse we have kVA, and this D here stands for displacement. What that means is that's the two-dimensional but basically 60 hertz part of your apparent power. Okay? Now let's add in harmonics. It's not watts, it's not VARs. It goes like almost like in the third dimension, this z-axis here. So if I have harmonics, if I have a lot of harmonics, notice how my kVA total now becomes a lot bigger. And so when I look at the kVA, which again is volts times amps, my current has gone up by adding in these harmonics. So if we're going to, let's say, eliminate kVAR here, we get closer to kVA equaling kilowatts. That's basically when we do things like power factor correction, get rid of the reactive power from inductive loads. If we're going to reduce harmonics here, that's going to reduce this kVA total. So in reducing harmonics here or kVAR here, we're not really changing the watts at all. We're just changing the kVA. And that's really important to understand, because what do we pay for on our bill? On our bill, we pay for kilowatts, or the amount of power that we're using. And for commercial customers or large industrials, we pay a kilowatt demand. And there's lots of information in our videos about that. There's kilowatt hours, which is basically kilowatts over time. So these two are directly related. The third part, which is related to kVA, is based on the power factor. And the power factor is kilowatts over kVA. And I'll draw that out for you in a minute. But for the 60 hertz part, the utilities only bill based on the displacement power factor. And again, this is important. So where does this leave harmonics? Let me draw this out for you and explain on that three-dimensional chart how it works. So if we take a look at, again, on the x-axis kilowatts, on the y-axis kVAR, and here's kVA. If the utility doesn't bill us for power factor penalty, and again, power factor equals kilowatts divided by kVA. If the power factor was 1, for example, our kVA and kilowatts would be equal, the kVAR would be 0. If they don't bill us for kVA and they don't bill us for power factor issues with extra kVAR, then this becomes irrelevant. They only bill us on kilowatts and kilowatt hours. So kilowatt demand and kilowatts over time. If we add in this third dimension here, which again is our harmonics, how does that affect our kilowatts? It really doesn't, except in the same way that the kVAR does. And I'll explain that in a minute. But it really doesn't affect us. What it does affect is this bigger kVA here, which is kVA total. Okay? So if we're affecting kVA total, how does that affect our power factor? Our power factor total is kilowatts divided by kVA total. And as you can see, since kVA total is bigger than this other kVA, our power factor goes down. But I'll reinforce the fact that utilities bill on this power triangle. They bill on, and there's historical reasons behind this I can explain in another video, but essentially they bill on that power triangle. They don't bill on the Harmonics one. So they're not going to bill you for Harmonics. Where this does come into play though, there is a small little caveat on all this. So if I have a transformer and I have some cable length and stuff here, and I come down here and I put a motor on and I have current flowing through my system. What does that current do? Well, it affects my load. I'm paying for kilowatts that I'm using to power the load, but I'm also paying for the losses along the way through the transformer, through the cables. The I squared R losses equals watts or kilowatts, okay? So when I look at this, then I am paying for losses that come down through here for my VARs, kVARS, and I'm also paying for my losses according to my harmonics, okay? So as I mentioned before, because kVA is proportional to current, any additional current I put in my system creates additional losses. But a lot of people over-exaggerate that and say that those losses are huge, when in fact they're somewhere in the neighborhood of 1 to 4% kind of maximum numbers for typical power systems. So as we look at that and basically consider power systems and how that affects us, there's losses in the actual cables and conductors and transformers and so forth. But there's another loss that comes in motors especially, and that's where we have things like negative sequence currents. But again, these numbers are very small compared to your overall losses on power systems. Again, if we're in the 1 to 4% range, I've been told that essentially lubricating a motor probably makes up more of a difference than the losses that you get from something like this. But at the end of the day, how do harmonics affect your power bill? They don't directly affect it because we're billed on power factor displacement, which is 60 hertz only. How they can affect it a little bit directly, but more indirectly, is through the losses. And those numbers are in the 1 to 4% range. So if you put a harmonic filter on, for example, and you eliminate all your harmonics, you can save 1 to 4%. You can't save 20% of your bill just with getting rid of the harmonics. But in the same way, you could get rid of a power factor penalty and save 20% of the money for your bill. You can relieve some of the money when you do power factor correction with harmonic filters, but not the harmonic part of it. So again, it's all related, but just make sure you understand that the part on your bill that you're going to save is losses or power factor compensation. And because harmonic filters do both power factor and harmonics, sometimes there's money to be saved, but not from the actual kilowatts or kilowatt hours. Seems a little confusing, but it's really not that bad if you think through it.